Hello, everyone. Um, if you are currently online and you can see and hear me, please send a message to the chat. As long as you're a subscriber, you'll be able to post to the chat. Please send a message to the chat if you can see and hear me. Hello, please send a message to the chat if you can see and hear me. All right, thank you very much, Matt. We'll begin immediately. So you know my name already, Daniel. I represent Imole Solar in this training. For throughout the course of the training, you'll be interacting with me. If you have any question or you want to make any comments, kindly send it to the chat. And somewhere between the meeting or during the meeting, sometimes during the meeting, I'll send you the attendance link. As you know, the attendance is mandatory, and the PDF has just been sent to the group containing your matriculation number. Throughout the course of this training, that matriculation number um, is what you'll be using to interact with us. You have to go and check it and make sure you note it down. Okay, thank you. Let's begin immediately. Today we'll be talking about basic electronics. As a solar engineer, your work is not just to climb someone's roof and install panels. Um, we um, Part of your work is understanding the mathematics behind solar engineering. Because if you don't know the math behind it, then you're not going to be a very good engineer. So today we'll be talking about the mathematics behind being a solar engineer. Uh, the topic is basic electronics. Some of you, well, most of you actually are from engineering, particularly School of Electrical, I don't know what they call it now, but basically EEE, ICT, CP, and so on. But some of you actually are from medical engineering, even all the way to SENT and entrepreneurship department. I really applaud that because it shows dedication. So let us begin. Basic electronics. So don't mind the board. The board is just here for you to get some details as we are going through the training. Maybe some things that I can't say with my mouth. I'm just going to sketch it on the board for you. So first, let's talk about concepts. The first concept I want to introduce you to is voltage. Now, some of you, or most of you, probably all of you know what voltage means. But then you need to know what it means in a theoretical sense. For example, if I ask you what is voltage, some of you might say it's power. It's not the same thing as power. Voltage, it's like a level at which power is produced. First, let's establish something. Electricity. Electricity is the flow of charge through a wire, and then that flow of charge can be used to power various things, such as maybe charge a battery or power the entire room. Now, current is the flow of that charge. We don't just say flow of charge. When you say flow of charge, you are practically talking about current. Now, what is voltage? Voltage is like the level at which that charge is produced. For example, let's say, okay, let's say you have a, okay, I'm trying to look for a very good example to this. Okay, let's use the water analogy. I find it to be quite instructive. Let's say you have a big storage tank. Most of you know what a storage tank is. That huge tank that is usually on top of a house that you store water in. Let's say you have a huge storage tank. Now we have the small version, the medium version, and the large version. Now the small version can produce water as well as the large one. In that sense, voltage would be the force at which that water is being produced. So let's say you turn on. Okay. Let's put it this way. Let me backtrack a bit. Sorry about that. Let's say you have storage. Sorry, I don't think this thing is as clear as I want it to be. Let's say you have storage tank. This is the first tank. This is the second tank. This is a small tank, and this is a larger tank. Now, you know, in a storage tank, you use pipes to get water from them. You can have a small pipe, something like this, or you can have a large pipe, something like this. Now, this tank, from a logical sense, let's say they represent a power source, say a battery. Assuming these tanks are batteries. This is a small battery, and this is a bigger battery. Now, if I were to plug this particular what's it called now? Pipe to this tank, it will produce water. It won't produce as much water as if I were to plug this particular one into this tank. Now, voltage is the size of this pipe. Power sources can produce a finite amount of energy. Let's say this guy has 200 liters and this guy has 400 liters. If I plug this into this, it will take longer for the water to run out as if I plug this into it. So a storage tank containing 200 liters of water, and I'm plugging a small pipe. It might take about 5 hours, sorry, not even up to 5 hours. It might take about 20 minutes for all the water in the storage tank to run out of it, and for us to get all the water from it. But if I plug this bigger pipe to it, it will take way less time, maybe about 5 minutes for me to get all the water from it. What I'm trying to tell you here is that a storage tank is like an energy source. It has a finite energy. The total energy I can get from it is 200 liters. But depending on the voltage at which the battery, storage tank in this case, produces that energy, that can help us determine how long it will last. I'm sorry if I'm coming off as kind of confusing, so let me just take a step back and summarize. In electricity, you have first the energy source. Now that energy source is finite. When I say it's finite, what I mean is that there is only a certain amount of energy that can be stored in it. I'm trying to make a practical analogy between energy or electricity in general and the storage water system, the one we use at home. This is a storage tank. We are assuming it's 200 liters. I don't know if it's actually 200 liters in real life. We are assuming it's 200 liters. No matter how we try to get water from this tank, it will always give us 200 liters. The only difference is that it might give us 200 liters in about 5 minutes, or it might give us 200 liters in 20 minutes. This tank is sealed. Now, these two are pipes. This is a small pipe, and this is a larger pipe. If I plug this small pipe to my storage tank and I turn on the tap, let's say it takes about 20 minutes for the water in this tank to be evacuated. But if I were to use a larger pipe, it will take less time, say 5 minutes. From the analogy of this water system, the storage tank will be the energy source. The capacity of the storage tank, note that word, capacity, 200 liters, will be the power. Let me list them so we don't get fully confused. First, we have voltage. Second, we have current. Third, we have power. Fourth, we have energy, voltage, current. And fifth, we have resistance. So we have voltage, current, power, and resistance. We have a tank, say 200 liters capacity. It can contain 200 liters of water. From the analogy, okay, let me go ahead and just cross that off. So let's say we have this tank here. This is the water tank. This tank can give us 200 liters of water. Now, 200 liters is like the capacity of the tank. Now, that 200 liters so just beside the tank, let me draw a battery. Now, that 200 liters capacity of the tank will correspond to the power of the battery. Power, another word for power is capacity. So when I say this tank is 200 liters in capacity, it's also the same thing as saying the battery has a 200 watt capacity. Hope you are following me. Capacity is the same as power. So I'm trying to draw a parallel between a water system and a battery system. I know they are not the same thing, but it's just a way for me to explain it better. Please feel free to add comments in the chat section. I can see them live actually. So whatever you do, put there, I might be able to respond to it. Yeah, I see that. So we are starting with power. One more time, the capacity of the storage tank. This is like a storage tank, and this is a battery. I'm trying to draw a relationship between them. We're saying the capacity of the storage tank is 200 liters. In terms of electricity, that 200 liters is the same thing as saying 200 watts of power. So that tells us that power is the total amount of energy that an energy source or a battery can store. Some people, you can also say power is the rate of doing work, but this is electricity. We're not dealing with mechanical motions or anything like that. We'll be talking strictly in terms of electricity as related to our solar engineering stuff. So let's move on. I also made an analogy and said, okay, what if you had I said, now that we have a tank filled with water, what are we going to what if we want to get that water out? What do we use? We use a pipe or some kind of way to get it out. So let's say we have two options. Let's say we have two options. We have a small pipe or a narrow, and we have a larger pipe. Now this pipe, this is a small pipe and this is a larger pipe. When we connect the pipe to the storage tank, if we were to connect the smaller pipe and just turn it on, our goal is to get all the water out of the storage tank. If we were to turn on this pipe, it means that let's say we turn it on and it took us about 20 minutes to get all the water out of the storage tank. If we were to remove this pipe, fill the water back, and connect it to this pipe, it's going to take us less time. Maybe it can even take us about 5 minutes to get it out. Why is that? It's because the pressure at which you take it out has changed. Take it out through this pipe, assuming the force at which it's using to get out remains the same. If we take it out through this pipe, it's come out at a higher rate than if we take it out through this pipe. Now, let's coin our terms appropriately. In terms of power, I said power is like saying capacity. But when it comes to voltage, it's like saying the rate at which the charge or water is coming out. If we were to take the water out through a small pipe, it will come out at a lower rate than if we were to take it out through the large pipe. The rate which is coming out is what we call voltage. Voltage essentially is the rate at which you can take and you can take charges out of a battery. Yeah, I hope you are able to get that. Now, when I say charges, in terms of comparing a battery to a water system, the charge in the battery will be equivalent to the water in the tank. So now charge is the actual thing that is stored in the battery. The total amount of charge in that battery is what we call power. The rate at which you remove the charge from the battery is what we call voltage. No, that is not quite right. Sorry about that. Voltage is just like the level at which you remove the charge from the battery. Let me just try to land somewhere. Now, the rate at which the water is flowing out of the tank is what we call current. Because sorry, hold on. We know that I equals QT. Sorry. Okay. Current is the rate at which sorry, just give me a sec, please. I might have missed something up. Okay, let me backtrack a bit. The voltage is like the level at which you take the charge out of the battery. Now, the current is the flow of charge. Voltage is the level at which the charge comes out of the battery, while current is the actual flow of the charge. Power is the total amount of charge stored in the battery. Energy describes usage. When we say that, what is the energy of the battery? Energy isn't actually something that is stored, neither is it a unit of measuring the actual stored charge. Energy is basically power times time. Energy is how do I say this? Is the total amount of energy is the total amount of power used over a particular amount of time. Let me take us away from the whole storage stuff because it seems to be confusing. So these are the terms that are relevant to our study in solar engineering. The first term being voltage. Voltage is the level at which the charge is produced. Charge is what is actually stored in the battery. Current is the flow of that charge out of the battery. Power is the total amount of the charge stored in the battery. Energy describes the charge we have used so far. So let me take that again. If we have a battery, what is actually inside the battery is the charge. The level at which we let those charges come out of the battery is what we call the voltage. The total amount of the charge stored in the battery is what we call power. The total amount of power used over time is what we call energy. And that is why the formula of energy is equal to power times. Energy isn't really something very much in solar engineering. In the field, on site, we don't usually talk about energy that much. The only time we use energy is when we are calculating time, because it has this special time in it, this special component in it called time. Energy allows us to calculate the time, maybe the time it will take to charge a battery, or the time it will take to use a battery. Lastly, I would like us to talk about resistance. And before I talk about resistance, I want to apologize for being a bit confusing there. And for the sake of clarity, let me go through it again. In solar engineering, we have energy sources such as battery, the sun, the solar panel, and so on and so forth. When it comes to electricity in our field of work, these are the terms that we consider very important. Let me just add charge to the top of the list. I hope you're taking notes because of the test that will come later on. Charge is what is actually stored inside the battery. If you were to break the battery, you won't see it because it's a solid state kind of thing. Charge is what is stored inside the battery. But those charges have to come out of the battery for us to use them. The level at which they can come out in the low level or in a higher level. The level at which they come out is what we call voltage. The flow of that charge, the actual flow of the charge out of the battery, how fast they are flowing out of the battery. Let me use that time. How fast they are flowing out of the battery is what we call current. Power is the total amount of the charge stored in the battery. For reference, this current we usually represent with this I, and the formula can be I equals to Q over T, the rate of flow of charge. Power is the actual amount of charge stored in the battery. And the formula for that is P equals to IV. Sorry for the tilt. IV, which is like what power is current times voltage. Energy is the amount of power or the amount of power used over a particular period of time. That is why energy E equals to P times T. And resistance. Finally, let's talk about resistance. When I say resistance, is like the word is like the word actually the word itself is explaining itself. When I say resistance, is like what is limiting the flow of charge. That is, resistance will always work against current. But there are some formulas that are actually important that I'll need to take you through. So this formula I want to write is what we use to calculate resistance, but we rarely use it in the field. In fact, after this, I'll show you the formulas we usually use in field, which is important. But this one is really important, but I will tell you why you should take note of it now. R, which is resistance, equals to PL over A. Now, R here is the resistance. This here is what we call resistivity. L is the length and A is the area because of the wire. I'll say this now, very important. The wire you use in your installation is one of the most important parts of your job. If you use the wrong wiring for your job, you will have a lot of issues with it. So let's take, for example, we have this wire. Resistance is what we want to know. We want to keep resistance as minimum as possible, because if resistance is too high, it's going to cause a lot of energy wastage. Because a guy pointed it out in our last meeting that he said, he said P, which is power, equals to I squared R. If we were to solve this for I, you will see that I equals to the square root of P over R. Sorry about the tilt again, which will mean that current is inversely proportional to resistance. When I say something is proportional to something, if something is directly proportional to something, it means when one increases, the other will also increase. But when I say something is inversely proportional to something, it means when one increases, the other will decrease. How will you know if something is directly or inversely proportional? Just make what you want to, what your main term is the subject of the formula, and whatever is the numerator is directly proportional, whatever is the denominator is inversely proportional. So from here we see that the higher the resistance, the lower the current we get, and we want the charges to flow. The flow of charge is current. If we have a lot of resistance to that flow, the current will be less, which is not good, which is like wasting a lot of energy through this equation. So now, how do we make sure resistance is minimal? Because if you use the wrong wiring in an installation, the resistance will be high and you're going to be wasting a lot of energy. Eventually, the customer will come to you and complain that, oh, this thing is not working, the battery is bad, it doesn't last more than 30 minutes, all those kind of things that those kind of complaints people usually have for solar. Now, looking at this equation, it tells three things that affect resistance. The first one is the resistivity. This term here that looks like P or E. This term resistivity. What is resistivity? Resistivity is the it's a intrinsic property of an element. When I say an element or a material, we have different kind of wire materials in solar. We have copper, we have aluminium. Those are the two that are most popular. Metallic elements. We have even iron. Sometimes people use iron for their wiring. We have different kind of materials in solar. Now, depending on the material you choose, these materials have different resistivity value. Copper has a different resistivity value than aluminium. So you need to choose because resistance is directly proportional to resistivity, which means you need to choose a material that has a very low resistivity. Because the lower the resistivity, the lower the resistance. The higher the resistivity, the higher the resistance, because resistance is directly proportional to resistivity. So you need to choose a material with very low resistivity. Now, I'm going to be throwing assignments to you as we are having this lecture. I'll note them down. You have to submit it at a specified time. When I'm done with the lectures, I'll tell you when to submit it. The first assignment is for you to research the materials used for wiring in solar and their resistivity. Research different metallic materials and metallic elements used for wiring and their various resistivity, and then figure out the best one to use. The next thing we want to consider is length. What does this formula tell us? It tells us that the higher the length, the higher the resistance. Remember, from this formula, our goal is to keep resistance as low as possible. Because if we have a lot of resistance, we'll be wasting energy and the battery will not charge. So this tells us that the higher the length, the higher the resistance. Now, our goal here will be to keep length as minimum as possible. Let's say I have a wire this long and I have a wire this long. If I use this wire, I will be able to save a lot of energy as if I use this wire. Let me explain this more clearly. Let's say you are doing a solar installation for your house. Let's say you live in a bungalow and then you use a particular length of wire to connect the panel to the battery, and then everything works fine. But let's say after a while you move to a 10-story building, if there's such a thing, and then you install the panel on the roof of that 10-story building, but then you are living all the way downstairs. It means you're going to have to use a longer wire to connect the panel to the battery. Basically, this means that your length is going to increase, which means your resistance is going to increase. That means you won't get as much energy from the panel. Your battery will take longer to charge, if it's even going to charge at all. There's even a length you're going to reach where you will not even see the energy enter the battery again. So this formula holds up. We have talked about resistivity, we have talked about length. Let's talk about the last one, area. This is the cross-sectional area of the wire. Let me just say thickness. That's something more relatable. Let's call this thickness of the wire. This tells us that the higher the thickness, the larger the wire, the lower the resistance. Also measured in millimeter square, we call them mm. There's a 1 mm wire, which is the normal wire you see used in wiring a house. There is 2.5 mm, there is 4 mm, 6 mm, 10 mm, 16 mm, and so on and so forth. This formula tells us that the thicker the wire, the less resistance we are going to get. So if we're to use a 1 wire to connect panel to battery, like one guy did that I helped fix, there was this customer that I was called to help fix things, first the solar. The engineer that helped him do his stuff connected his panel to his battery using a 3029. And the 3029 is a 1 wire. So that means that the rotational area is so small that the resistance is so large. He kept saying the battery is not charging. Then he had to change the wiring to 6 Immediately he changed it, everything started working fine. Why am I explaining all this complex, all this mathematics to you when all you want to do is to just install solar? It's because this training is not just to teach you how to install solar, it's to teach you how to be independent, how to be a professional. You need to understand all this mathematical stuff for you to like make good judgment in the field. If you install something for someone and the customer calls you that it's not working, well, even if you know this, the customer will never call you. In our company, customers don't call us that our stuff is not working. But if you were to be called that is not working, this knowledge will help you will help you debug it, will help you figure out what exactly is wrong with it. Now we have talked about this resistivity. I hope by now you're able to understand all the basic terms in solar engineering. Let's move to the next part of the training and we'll be done very soon. Good. The next part of the training is equation. This is just like the basic equations you need to know. The first one is the most popular one. You already know this one, Ohm's law, which says V equals to IR. Right? I don't need to explain this. You already know what it is. But the reason why you must know it is you might need to calculate some things in the field that has to do with this. Now, anything that has resistance in it, we don't usually use it anyway, but it's just good to know it. The next thing you need to know is the formula for power. P equals IV. Power equals to current times voltage. The next thing you need to know is energy. E equals PT, which means E equals IVT. Now, this one is very, very important. The next thing you need to know is how to calculate time. Now, before you were admitted into this training, there was a question that was supposed to be on form. Most people feel that question. Some of you here got it right, not all of you. The reason why most people failed it is because they were overthinking it, using different analogy, trying to figure out the secret, maybe something that everybody's going to miss. So it's actually really a simple question. We're going to use this in a bit. Yes. Now, V equals IR, Ohm's law, P equals IV, E equals PT, or E equals IVT. Let's use a scenario. Let's say we have a panel that produces 200 watts. Let's say we have a 40 AH battery. The 40 AH battery, AH is amps hour, which means this already has current and time in it. So how long will it take a 200 watt panel to charge a 40 AH battery? That's what we want to calculate now. One thing you should know in solar is that to calculate time, it is just energy divided by power. From this formula, if you were to make time the subject of the formula, time equals energy divided by power. Energy is kind of like where the power is going to, and power is the source. This is like the receiver and the source. So the power is going to the battery. Here we have 40 AH. What else do we know about energy? We know energy equals IVT, which means the formula or the SI unit of energy is going to have A in it. Okay. It's going to have A, V, and sorry, don't let me confuse you with that. Energy is current times voltage times current and times time. Here we know that here we know we have a battery of 40 amps hour, which means this unit already has current and time in it. All we need, what all that is remaining is voltage. Now, there is one thing you need to note in solar: most of our batteries are rated 12 volts. Most of them are rated 12 volts. If you want a system, you just connect two 12 volts in series. If you want 48 volts, connect four 12 volts in series. So that's the way we increase or decrease the voltage. But fundamentally, all our batteries are assumed to be 12 volts, except lithium. We'll get to that in a bit anyway. Now, a 40 um, battery, if we were to multiply this by voltage, we'll be able to get the energy. This current, which is this, the time, which is this, all we need, what is remaining is voltage. 12 is going to be what? Can someone calculate 40 times 12 and just send it to the chat? I think that should be 480, if I'm correct. So that should be 480 joules. That's the energy. So we come here and say 480 divided by power. Power here being 200. So 480 divided by 200 is what? Please send it to the chat. So if you were to calculate 480 divided by 200, you'll be able to get how long it will take the battery to charge using the 200 watts panel. Of course, this is a bit different for, yeah, thank you very much. Of course, this is a bit different for when you consider efficiency. Now, this formula, this equation here assumes that efficiency is 100%. When efficiency is not specified, you can just assume it's 100%. But okay, someone wants me to recap. Just a minute. Power equals to current times voltage. Energy equals to power times time, or IVT. If we were to substitute the formula for power. Okay. Now, I gave an example. I said, let's say you have a 200 watts panel. How long will it take you to use a 200 watt panel to charge a 40 Ah battery? If we were to use this formula and make time the subject of the formula, time will be equal to energy divided by power. Now let's calculate the energy of the battery. We have been given the battery being 40 Ah. By the way, batteries are rated in Ah. Sometimes they're rated in watts. But when it comes to lead acid battery, we rate them in Ah. We'll get to that in later chapters. Now, this 40 Ah already have current in it, and it has time in it, which means all we need to do really is to multiply it by the voltage. Lead acid batteries such as this are rated 12 volts. Basically, we assume all lead acid batteries are 12 volts that we use in solar, by the way, not all the smaller ones that are using torchlights. Which means we can say this 40 times 12 over power, which is 200. 40 times 12 is 480 divided by 200, and someone calculated it to be 2.4, which means it will take 2.4 hours for the for the battery to be fully charged. Now, in this case, I'm assuming that we are in an ideal situation, which means we assume the world is perfect and our battery and our panel is 100% efficient. But in real world, that is never the case. Maybe there's a dust on the panel that's reducing the efficiency, or the sun is not in the right place. maybe you bought a low quality battery or something else. Batteries generally are not that efficient. In fact, lead acid batteries are usually between 60 to 70% efficient, while lithium are around 90% efficient. But then again, let's say we were given that, okay, the panel is 30% efficient. So let's say the panel is 30% efficient and the battery is 80% efficient. How will we go about calculating the time it will take to charge this time around? Well, it's simple. What you just do is take what you were initially given, which is 200 watts, multiply it by 30%, which will be zero point 0.3 to get your new power for the panel. Take your 40H, multiply it by, what's it called now? 65% to get your new rating for the battery, and then use the same formula to calculate time. Yes. So I think that concludes our training for today. Let me give one final recap before I finish. First, sorry for the confusion at the beginning of the training. This is the first time we're having. I'm sure it won't happen again. So let me just give a brief recap. We talked about two things today. First, we talked about fundamental concept in electricity, which is essential for you to know as a solar engineer. Then we touched on the formula or equations that are relevant to our field. Of course, there are others, but they're not really relevant to our field. First, we talk about charge. We say charge is that thing that is actually stored in the battery. Maybe you can call it electrons or something, electrons and ohms. But what is actually stored in the battery is what we call a charge. What is actually coming from the is what we call a charge. Next, we talk about voltage, the level at which the charge flows out of the panel or the battery. The level is what we call voltage. Next, we talk about current. Current is the rate at which that charge is flowing out of the battery or the panel. Now, what is the difference between voltage and current? Voltage is the level at which the charge flows out. So let's say the charge I don't want to use another water analogy so I won't confuse you. But voltage is the level at which it flows out of the battery, and current is the rate. When I say rate, it means how much charge flows out of the battery within 1 second. That's what current is. That's why we have this formula for current: I is equal to Q divided by T, where Q is the charge and T is time. Power is the amount of charge stored in the battery, and power is the product of current and voltage. Energy is the power used within an amount of time. Resistance is what says, you know what, you're not going to get this charge. I mean, the charge, the current coming from the battery is supposed to go to where we use it, but resistance is like the man standing between the battery and you and telling the battery or the charge not to go to you, and instead it's just throwing it out, wasting it. Then we talked about the formula for resistance, which is R equals to PL over A. And I told you what this means and how they affect resistance. I gave you the first assignment, which is for you to find out what resistance, the materials used for wiring, and what their resistance value is, and the best material to use for a solar wiring. And I give you a second assignment, or if I didn't, I'm giving you now. Find out the different sizes of wire in mm. I told you 1 mm, 2.5 mm, 4 mm, 6 mm. I want you to find out the different sizes. And I think we'll stop there. Thank you for joining today's live session. We'll be having the next one um, next tomorrow, 9 o'clock. Let me send the attendance link to the group for you to. So I'm going to send the attendance link to your live chat here, and you should use your matric number to fill it. Use your Imole matric number, not your personal matric number. All right.